So that was a little weird. I don't know what just happened. It just entirely decided to crash the login. And, yep. It's the first time it's done that in a while. Hmm. I don't know if we had a power blink. No, that's not possible. It couldn't be a power blink because I have this hooked up to a UPS. So. Let's try that again. No, don't run an ad, jerks. Literally just did one. It's only gonna let me snooze 3 times, so oh well. Anyway. Yeah, I don't know what just happened there. So weird. So, right. Yeah, so the reason that all works is because it divides 2 and 5 both divide 10. Yeah. You serious? I got another alert for it. Alright, well, hopefully that will at least stave it off for a bit. Should not be showing alerts for ads for at least another 20 minutes. But, since the crash was apparently my fault, can't get too upset about it. Okay, anyway. Yeah, sorry again for all that. That was very strange. And if anybody has not made it back. Yep. That is one of the very weird things about like doing bases and stuff like that. With a base 3, 1/3, for example, 0.333 repeated in base 10 is just 0.1. Right. Whew. So the way we have it is you can have whatever integer portion you want over here, don't care. And then we have plus this sum as j goes from 1 to n, where we have a sub j are going to be our coefficients, times 10 to the negative j is going to get us what position we're in at each place. A sub j will be only the digits 0 through 9. And then n will be finite. So it has to finish at some point. Okay, so rigorously, we can at least say that this will end up being like this whole section here could end up being whatever number it is. Hang on, what does it want? It said represents a rational number whose denominator contains no factor other than 2 or 5. Yeah. Okay, can be expressed. As some integer. So a divided by 10 to the n, where a is some integer and n is the number of positions after the decimal. So right? So 10 to the n is just how many positions we're moving our decimal place. Again, it has to be finite. Because it will be a terminated decimal. Who knows how long it's going to take to get there, but nonetheless, it will be a known factor. Okay. So then excuse me. With that, any such rational must be expressed as a terminated decimal. I mean, we can reverse the argument. That's uneventful, uninteresting, but still. All right, so if it starts with only 2's and 5's as denominator factors, then we've got some a divided by 2 to the m times 5 to the n. And ridiculously, let's assume that m is greater than n, or m is less than n. I guess we need m's equal to n as well. Yeah. Thanks to anybody who stuck around after the crash there. Jeez. Don't know what happened. Okay, so if m is equal to n, this is the easy one, then this is just going to be a over 2 to the n times 5 to the n, which is a over 10 to the n which has a terminated decimal after n places. If m is greater than n, then we can end up doing this as just a times a's, or m is greater, so 2 to the m times 5 to the m. Let's step that back. So this would be like 5 to the n times 5 to the m minus n. And then we multiply that on the top as well, 5 to the m minus n. Through multiplication, we add their exponents, so that's going to be a times 5 to the m minus n over 2 times 2 to the m times 5 to the m, which is a times 5 to the m minus n all over 2 times 5, or 10 to the m. At that point, it becomes the same as all of our previous arguments. Right, which ditto. Alright, in this case it's just going to be that it's the same termination, but it's going to be after m places instead of n places. And then again, if m is less than n, again without loss of generality, we could do this with any such factor, but nonetheless. A over 2 to the m times 5 to the n is going to be the same as a times, this is going to be 2 to the n minus m over 2 to the n minus m times 2 to the m times 5 to the n, which is then also going to come out nice and easy, a times 2 to the n minus m divided by 2 to the n, 5 to the n. And likewise again, right, this is going to be terminating our decimal after n decimal places. I'm feeling good about it. All right. Example 4. Positive rational numbers may be arranged in the form of a simple series as follows. Right, this is going to be the same one that we did for like the Okay, rational numbers may be written as a sequence. Again, this is 1 over 1, 2 over 1, 1 over 2, 3 over 1, 2 over 2. Nope. Yeah, that's right. Jeez. 1 over 3, 4 over 1, 3 over 2, 2 over 3, 1 over 4, and dot dot dot. Show that P over Q is the 1/2 P plus Q minus 1/th. Oh no, times P plus Q minus 2 plus Qth term. Oh, didn't do it. Well, anybody who's here, thank you for sticking around. We'll be right back because this ad break will end in about 30 seconds. It's already almost half over. All right, we're back. Jeez, sorry about that. Yeah, for some reason it did not take again. Good news, pre-rolls are still off for the next 56 minutes. So I guess that's good for anybody who's coming in new. Okay, so show that P over Q is this term, this numbered term in the sequence. So potentially we could do some sort of induction. I don't know if we want to do it that way. Alright. Alright, so this is a 1/2 1 plus 1 minus 1 times 1 plus 1 minus 2 plus q. Okay, is going to be equal to, this is 1/2 times 1 times 0 plus 1 is just equal to 1. So, looking good so far. And like, I know that if we're doing actual induction, we only need to show that this works for, you know, the n plus 1th term given the nth term. But at the same time, want to at least attempt to show that it works from for all the ones that we have here, or at least a majority of them, if I can see where the pattern's going. Maybe I mean, I can see where the pattern's going, but if I can find a better way to express it, that's pretty awesome. It is also 11:45 here, so we're starting to get a little bit tired. It's alright. Okay, so this is going to be 2 plus 1 minus 1. And 2 plus 1 minus 2. Plus 1. 1/2 times, the first one is 2, second one is 1. Plus 1. This is going to be a 1 plus 1 gets you 2. Cool. Alright. 1/2. 1 plus 2 minus 1. Those are the same terms. Times 1 plus 2 minus 2. Again, same terms. And then this one is going to be a plus 2 at the end. This is going to be 1/2 times. This is going to be a 2. This is going to be a 1. So 1/2 times 2 times 1 plus 2 gets us 3. Alright, 3, 1. 1/2. 3 plus 1 minus 1 times 3 plus 1 minus 2 plus 3. Alright, 3, this is a 1/2 times 3 times 2 plus 3. It's going to get you 3. Oh, definitely not. No, no, sorry. It's a minus. Hang on now. Why did I get 3 plus 3 equals 6? That's not going to work. Alright, where'd I go wrong? P plus Q. It's going to be a 4 in both of those cases. Oh, Q's only 1. Pfft. Jeez. Alright. There we go. It's a plus 1, not a plus 3. Okay, so 3 plus 1 is 4. Right, so this is going to... P plus Q is going to be fixed for that number of terms. And then Q is going to start from 1 and then work its way up to whatever the maximum is going to be for that row, level, whatever we want to call it. Okay. So if we are to do this in general, right, given P plus Q minus 1 times P plus Q minus 2 minus Q, or not, plus Q. We have a few different ways that this could go. Either we increment within the partitioning or the arrangement, however we want to call it. So in every case, P is going to become P minus 1, and Q is going to become Q plus 1. So P minus 1 over Q plus 1, right, is going to be equal to P minus 1 parent, nope, P plus 1 plus P minus 1 plus Q plus 1 minus 1, man, times P minus 1 plus Q minus 2 plus Q plus 1. Okay, so we get a 1/2. This is going to be P plus Q, the minus 1 and the plus 1 go away, so it's just P plus Q minus 1 times P minus, well, I missed one. Oh no. Alright, P minus 1 plus Q plus 1 minus 2 plus Q plus 1. Okay. P minus 1 plus Q plus 1, those go away, and we're still left with P plus Q minus 2. Plus Q plus 1. And that's going to be our n plus 1th term. Which the only difference between the two, right? These are all... oops. So these are in accord with the one up above, right? The only difference between the original up here and our n plus 1 here is that we have a Q plus 1. That's the only thing that's different between these things. Okay, so if we're within a partitioning, then we end up just adding 1 to Q in terms of its individual position, and therefore we get what we're looking for. Okay, but the other option we need to increment to the next partitioning. This is going to be significantly harder, but it's not too bad as far as I can think. So if we increment to the next partitioning, we're currently on P is equal to P is going to be equal to, is it the Q is going to be 1. P plus Q minus 1. Hardly fair. How do we describe this? It's like it's going to be the maximum value that we're going to get for that group. Still don't know what to call it though. It's just the maximum value currently. Whatever it's going to be. Okay, so then the next one is going to be P equals 1, and Q is going to be the next number, so max plus 1. It's a terrible idea. Alright, because it's got to be part of the next group. If anybody's new, my name is Obi-Wan Pez. This is N Simplex Pachinko. Please go ahead and drop any questions you have about math in the chat, and we'll discuss. If that is actual problems, then we could talk about it. And if it's just questions in general, we've got plenty of opportunity for anybody to ask any sorts of questions they want. Okay, so... Alright, P goes back to 1 and Q increments to the next max. So that means that the current N value not literally, however... Oh no. Where's my dispenser? Now, I've been going by the handle of Obi-Wan Pez for a couple years, and it was once my friend found an actual Obi-Wan Kenobi Pez dispenser from the, what was it? Clone Wars TV show. And she was walking down the aisle of a store, and then just kind of went like, something's weird, and looked over and just saw an entire wall of my face looking all back at her. She was like, duh. Okay, well, obviously need to buy one of them for him. So she ended up getting me. I'm gonna see if it's back here somewhere. She ended up getting me this Pez dispenser, and I was like, that's just really cool and nice, and thank you very much. Somehow I don't think it's here. It's probably in our shipment. It's just in my desk. In which case, it'll be here in, you know, upwards of a couple weeks. Minimum amount of time might be like, you know, a week or so. That'd be really cool. I don't think it'll happen, but especially since we're hinging this on the United States Customs Service, finishing stuff ahead of schedule. No offense to them, but you know, they got more pressing issues than our stuff coming into England. Actually, it would be the English Customs Service, but again, they have more pressing things that they have to really worry about, rather than getting our random stuff through customs ahead of time. Why would they want to get things done ahead of time? Anyway, yeah, I think it must be in our stuff, so it'll be here in a few weeks. But yeah, so I have been Obi-Wan Pez on as many platforms as I could find. I've been something else, and the problem was that when it was based on my name, A, I don't really want to do that, and B, the thing that I had picked was really common. I'm not going to tell you what it is, but it was common because it, you know, had to do with a sport that I had done in like middle school when I created my first username. And yes, middle school was when the internet was invented, or at least when it gained mainstream popularity, and it wasn't just some Usenet on university campuses only. Yeah. I mean, these days, like, if someone were to, um, like, do an actual contract, obviously, I would have to sign my actual name to that contract, which has my name attached to it. So that would be dead giveaway, I guess. But at the same time, you know, I gotta sign my real name if I'm gonna actually make like contract money. So speaking of, I am going to be talking fairly soon with a solicitor, I think, about determining what the appropriate rules are, tax laws, etc., of possibly setting up my own business. I currently have a name set aside, and I'm working on it, so we'll see how it goes. But as somebody who made precisely $50 off of Twitch last year, the meeting with the solicitor is probably going to cost me more. Possibly several times more. But I do not want to run afoul of UK tax law while I'm an American citizen. Alright, anyway. So the new n is going to be, well, n plus 1. Okay. So this is going to be 1/2. Yeah. I mean, that's going to be a little obvious, but whatever. Right, so if P's just gonna be 1, Q's just gonna be max plus 1. And then here we get a minus 1. Times P is 1, Q is max plus 1, and minus 2. Plus new Q is max plus 1 again. Alright, so here these two, the plus 1 and minus 1 go away. And we get 1/2 max plus 1 times 1 and 1 makes 2 minus 2 gets us max plus max plus 1. This is going to get us 2 max plus 1 times 1/2 each. Uh-oh. I got 1/2. That doesn't sound good. Oh, that's max. Right, that's max squared. Jeez. Man, multiplication. Knock it off. Woo! All right. And it's not distributed. Wait, no, it is distributed. Let's go back, actually. Let's keep it this way, though. Okay. So, better point to be made. One of either max or max plus 1 must be even. So overall, one of those is going to be divided by 2, and it's not going to be a problem. And then we get max plus 1 over on the side. This is going to be, man. It's not of the form of the other thing. It's going to be terribly awkward. This is n plus 1 all over 2. So this is the sum of all integers up to our previous maximum, which is n. No, it's not the previous, it's not n. It's just the previous maximum number. All integers. That's weird. Right? So in this stack here, like it'd be 3 here, it'd be 4 here. This work? This was going to be the average value. It's adding up all. Okay, so I'm looking at this and I'm like, oh, it's finding the average value of, but it's not really. It's not finding a weighted sum or anything else for that matter. Right, it was, got us a 0 on the first one, got us a 1 for the next 2, and got us 3 for the next 3. Okay, let's start this layer over here. Okay, these are not going to be P and Q. This will just make it a little bit easier. Hopefully. Right, let's use capital. Okay. P is whatever P value it's going to be. Q is just 1. And then the next one is going to be P is 1, and Q is going to be P plus 1. In fact, I think that makes it too obvious, and it works very nicely. So this will be half times, right? Big P, the next one is going to be 1 time plus Q, which is P plus 1, right? Minus 1 times P plus Q is going to be 1 plus P plus 1 minus 2 plus Q is P plus 1 equals 1/2 times P plus 1 times P, just P, plus P plus 1. Okay, so we're in the same dilemma as before, it's just now I can actually see it. Again, either P or P plus 1 is even, so this is going to come out as an integer. This is like P squared plus 1/2 P. This makes it 3/2 P plus 1. Oh, 1/2. 1/2 P squared. Okay, so if P is even, then we get rid of both of the fractions. So P squared is going to be divisible by 4, and it multiplies by 1/2. It'll clear that stuff out, and it'll also produce an even number. plus 3 halves p is going to multiply out our 1/2. So it's 3 times a half of whatever. Again, if it was even, then that just gets us an integer. And we're at an integer plus 1. If it's an odd number, squaring it gets us an odd number. So it has a 1/2 in it. And then plus 3 halves times p is going to also be an odd number, which is also a half. It's going to have a fraction of a half in it. And then combining that one with p squared, the halves are going to add together to get us an even number, which then divides out our 2's. Yeah. So whether even or odd, we get an integer. That's good. There might be a more elegant way to state this as well, but it'll be okay. Not real. How's it going? So here, this was rational numbers may be written as this following sequence. So it's going to be 1/1, 2/1, 1/2, then 3/1, 2/2, 1/3, then 4/1, 3/2, 2/3, 1/4, then etc. So we always start with the integer value that this partitioning of that particular number has. So in the case of 4/1, 3/2, 2/3, and 1/4, they both add up to 5. It's like, how can you write these rational numbers as a partition, essentially? And then we said that P over Q can be expressed as this term. The 1/2 times p plus q minus 1 times p plus q minus 2 plus qth term. So I'm trying to do induction, and we proved that it works for a few of these. I just did the first 4. Worked out perfectly. And then we said, given this is true, then we need to show that this is the n plus 1th term. In this particular case, when we increment within a partition, so we go from 2-1 to 1-2, or we go from 3-1 to 2-2, or 2-2 to 1-3, etc., then we use this stuff here. Our p is going to become p minus 1. Our numerator are ticking down 1 every time, and our q's are all ticking up 1 every time. So that's nice and easy. I got a q plus 1. The only difference between our original and the new one is this q plus 1 at the end instead of a q. So therefore we've incremented by 1, and therefore the nth term became the n plus 1th term when we do that increment. Now, the other option is we can increment to the next partitioning, where our p-value starts at the maximum for whatever we got. So 2, 1, 3, 1, 4, 1. Q is then going to be 1. Oh, that's wrong. It's the other way around. Man. Damn it. Well, at least I caught that mistake, so thank you. I mean, it's going to be essentially the same problem, but ever so slightly different. Okay, so n plus 1 is going to be 1/2 times our p's were at, again, if we transition to the next one, our p's were at 1 and our q's were at max. P's are at 1, q's are at max. Then, when we transition to the next partition, P is now, or yeah, big P is now going to be little q plus 1, and big Q is going to be 1. Okay, so the next one is going to be P becomes q plus 1 plus q minus 1. Oh, no, 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 no. Don't do that. Well, actually. No, the new q is going to be 1. And I mean, this is the same thing. It's just rearranging what I had before, essentially. So now P is going to be, again, q plus 1 plus q is 1 minus 2 plus q, which is just 1. So 1/2 q plus 1 times q plus 1. Okay, so again, same thing as before. Good news though, I didn't have this extra out there. So is the original one just n? Because that is the... That's the sum of the first n integers. Or sum of the first q integers. Oh, that's weird. This looks like it's actually going to work, but now I'm angry about it. Okay, so you add up the numbers that come before it. So in this particular location, oh my god, it is! Now I need to figure out why. That's messed up, man. Okay, so if we look at all the places where we partition, where the partition moves up to the next layer, right? So 1, 1 moving to 2, 1. We look at this and we say Q, that last one, was going to be was going to be 1. So now this is going to be Q is 2 times 1/2 is 1 times 1 is 1 plus 1 is 2. So the next one after the last, Q is 1 is going to be 2, 1, and it's at n value 2. Then we bump down to here. We say, okay, given that the Q is 1 in this case, we're going to get, again, come on now. That's still 1 though. Okay, maybe that didn't make sense. Hang on. Where are we? No, we're here. Jeez. Okay, we're at 2. So then, the sum of all integers makes it to be 3, plus 1 gets us 4. Oh my god, it is. Oh, wow. Okay, yes. It's all the triangular numbers that are where the transition is. Right? 1, 3, 6. So at all triangular numbers plus 1, we get our n plus 1, those locations where we have incremented to the next partitioning. That's cool, and I'm angry about it. I don't know if that's a thing. Probably not. Oh well. Boo. Okay. I'll have to figure that out later. And like, of course it is, right? Because the first group has 1 thing, the next group has 2 things, the next group has 3 things, the next group has 4 things. So of course it's going to be triangular numbers. Right, these are n. Right, the nth terms for the partition change are going to be all those triangular numbers, and then plus 1. All right, that's cool. Okay, anybody have any particular questions that they would like to talk about with math? Otherwise, we can, you know, talk about stuff too. Okay. Pop over here for a sec. Natural number game. I'm on Fermat's last theorem, but like, yeah, I'm not going to be able to figure this out, so. Really? Oh wait, I just need to sign in, right? That's a thing. Upload. Haha, I can upload my progress. I'm really glad that that's hiding this window because it's got my name all over it. Completely didn't think about it. Load selected file. Really? There we go. Ugh. Well, that set us back a bit. I believe Fermat's last theorem is in Power World as the last one. So yeah, that set us back a bit. Okay, I need to figure out a way to get us back up there, and I'll get us back up there, and then maybe next time we'll do some more lean stuff, because that's also cool. Alright, well, thanks everybody for sticking around. We're going to go over to see Ian Stuckey, who is doing some math. Provided. Yeah, there we go. So Stuckey is doing some proofs type stuff. While group and co-root lattice. Very nice. I don't know what that means either. It's okay. Yo, thanks for coming in. We'll see you next time. We're going to be back on definitely Friday for some gamey type stuff, and also next Monday, our streaming group is going to be getting together and playing Good Job. So we currently have a Good Job game going that has a scorecard, and we're all trying to compete against one another with all of our switches and trying to beat each other's really awesome scores by breaking as little as possible. So we'll see how tragic this can end up. Alright, see you all later. My name is Obi-Wan Pez. This is N Simplex Pachinko. We're off to see Ian Stuckey. Have a good night, everybody.